Okay, hello everybody. Let's assume that that's the time to start our lecture. So as Alexey already told you last time, at this moment we have a small change. Not only the lecture is changing, but the topic is changing a little bit. So today we'll start actually analyzing asymptotics of all these fancy models that Alexey was speaking about. And our first guest will be the same model that he started from, which is Aztec diamond. So that's the picture on the screen. So we take this rhombus of large size, we tile it with dominoes, 2x1 dominoes, and we want to analyze, okay, what's happening when the diamond is very large. So first, it's always nice to have some simulation, to have some idea of what's really happening. And there is a very nice website of Patrick Ferrari that I recommend to you. And he has very nice simulations. So let me run one of them. I don't know whether it's perfectly OK. Oh, the button start is now not seen. OK. OK, so that's a growing sequence of Aztec diamonds. And at each size, you will see really uniformly random sample from this Aztec diamond. That's not exactly the same dynamics that Alexey was speaking about yesterday. So he explained how you can sample Schur process. That's a little bit different, but a close relative. And maybe in 3 lectures, we will discuss how exactly this simulation was made. Now it's important just to see the result. So this is an Aztec diamond of size 50 × 50 in the end. And you see that something interesting is clearly happening. So there is some circle which is clearly visible on this picture. And the aim of the lecture today will be to rigorously understand that indeed there is some circle appearing. So that will be our purpose. OK, that's a large picture. Let's switch back to a bit smaller one so that I can recall some combinatorics of this model. This one. OK, so that's now a bit smaller sample. So that's an Aztec diamond of size 5. So you can see some particles appearing here. Let me briefly remind you how the particles are being constructed. First, let me fix that from here and for the entire lecture, we will always be looking only on the uniform measure on the domino tilings of this Aztec diamond. So nothing else. Just there are finitely many of those, some power of 2, and we sample one uniformly at random. And that's what we want to analyze and nothing else. OK, further is some particle system which is in correspondence to this domino tiling. So let me briefly remind you how this particle system is being constructed. For that, first you introduce the checkerboard coloring, as here. And then you distinguish not 2 types of dominoes, but actually 4 types of dominoes. So the difference is that if you look at the horizontal dominoes, like this one, then there is one which has gray on the left, and another one which has gray on the right. So these are 2 types. Like there is one type, and that's the same type. Where is the second type? That's the second type. And similarly with vertical ones, there is one which has gray on the top here, and there is one which has gray on the bottom, like here. OK. There are altogether 4 types. Now, out of these 4 types, let's choose 2. One vertical and one horizontal. So for this drawing, I have chosen the one which has gray on top and the one which has gray on the right. It doesn't matter which 2 you choose because everything is symmetric, but well, let's choose this one. OK, now let's keep in mind only these 2 types of dominoes, and let's put particles on them. So we'll have particles of 2 colors. Green will be on gray parts of those dominoes, and yellow will be on white parts of these dominoes. And so we arrive at this picture. I'm not sure whether it's visible that it's green, but it is. OK, so in this way, you get 2 systems of particles, green particles and yellow particles. And if you look a little bit carefully in the combinatorics, then you will notice that if you draw sections along this diagonal, like this blue, and along this diagonal, the number of particles will be growing. Namely, on this first diagonal here, you have precisely 1 green particle. On the second diagonal, you have 1 yellow particle. On the third diagonal, you have 2 green particles. On the third diagonal, 2 yellow particles. On the third diagonal, 3 green particles, then 3 yellow, then 4 green, 4 yellow, 5 green, 5 yellow. So that's the combinatorics of this thing. And there is a bijection. So if you know the positions of this particle, then you can reconstruct the tiling in a unique way. OK, now what Alexey told you either on the first or in the second lecture was the joint distribution of these particles can be actually identified with what's called Schur process. Namely, there was the following picture. So you should think about arrows going up and down. So that will be an example for the case when n equals to 2. And on the screen, you have n equals to 5. So you have specialization here. Here there is a specialization with 1 alpha equals to 1. Here is a specialization with 1 beta equals to 1. Here again, 1 alpha equals to 1. And here 1 beta equals to 1. So you start with empty Young diagram, and you end with empty Young diagram. So we identify each slice of green or yellow particles with a Young diagram, and then their joint distribution is given by the product of the Schur functions. So that's a transition between, between green and yellow in one direction, that's in the other direction. So that was the picture. So does everybody remember what it means that we have a Schur process with this specialization? So is there a need to remind? Does anyone wants to be reminded? OK. OK, so let's remind. So what this picture means. Like, let's immediately draw it in more general settings. So you have empty set. Then you have Young diagram lambda 1. Then Young diagram mu1. Then Young diagram lambda 2. Young diagram mu2, etc. And then up to Young diagram mu n minus 1. Young diagram lambda n minus lambda n. And then ends with empty Young diagram. And we have some specializations. So rho 0 plus, rho 1 minus, rho 1 plus, etc. And it adds with rho n minus, rho n plus. Now what this picture means is that you have a probability distribution on all these lambdas and mu's. So altogether there are n lambdas and n minus 1 mu's. So we have 2n minus 1 Young diagrams altogether. And the joint probability for all these guys, lambda 1, mu 1, etc., lambda n, is equal to 1 over some normalization constant times you start with a Schur polynomial at lambda 1, and you specialize it with respect to the first specialization, which means that you just take this symmetric function and you apply a homomorphism. So the specialization is just a homomorphism into numbers. So you get a number in the end. Then you multiply by this Schur function, lambda 1 over mu 1. And you take the second specialization, so that will be rho 1 minus. OK, then you continue. So you multiply, it was lambda 1 over mu 1, lambda 2 over mu 2, lambda 2 over mu 1 of rho 1 plus, etc., until you reach the very end. So you have lambda n over mu n minus 1, rho should be n minus 1, n minus 1 plus, and finally there will be lambda n rho n minus.
I think in the previous lecture we had a lambda mu were interlacing, but the definition by 20.
Well, it really depends on the choice of the specialization. So as soon as you specialize to this odd-stick diamond, they again will be interlacing. But more general definition, you can say that you have arbitrary specializations, and then in principle they don't have to interlace.
But you are taking lambda 1 minus mu1. So
yes, exactly. So if rho is a specialization in one alpha variable, then automatically that is non-zero if and only if they interlace. But if you have something a bit more general, then it might happen that, you know, something more general happens. OK?
So we have the arrows going the other way.
Well, arrow here is just for pictorial reasons. So actually always in this picture, you always have lambdas larger than mu's. So that's my notation. So you can ignore the arrows. I think that Alexey was not even drawing the arrows. He was just drawing lines like up, down without arrows. So just I kind of treat it from left to right, but it's symmetric in fact. Yeah, so that's important, that lambda is always over mu. OK, so here we have two specializations. So this specialization is really one variable alpha equals to 1, which means that this thing is non-zero, that is this thing, if and only if this thing is a horizontal strip, which means that it have in each column it has at most one box. And this specialization is beta equals to 1, which means that this thing is non-zero if and only if the difference is vertical strip, which means that in each row there is at most one box. And that is kind of clear in this picture, that you can see that when you move like from here to here, then the green to yellow moves at most by 1, and that's your beta specialization. On the other hand, when you move from this yellow to these two greens, then this yellow can be arbitrary between these two greens, and that's the specialization alpha. OK. So the first thing that we want to do here, we want to reduce the dimension a little bit. We will rise it back a little bit somewhat later, but let's first reduce it. So instead of looking at the whole huge collection of Young diagrams, let's concentrate on only one Young diagram. So you want to restrict yourself to a single Young diagram, so maybe to this one or to this one. For that, we need a theorem which says what is the projection of this object called Schur process onto a single diagram. And that will be our theorem. That if you look at this joint distribution of all the guys, then the distribution of one lambda, so distribution of lambda k is given by the following formula, that probability of lambda k is proportional to Schur function evaluated at all the guys which are going up and which are on the left from lambda. So that's rho 0 plus rho 1 plus up to rho k minus 1 plus, and then multiplied by the same Schur function. And now you've taken all the arrows which pointing down and which are on the right. So that will be rho k minus union rho k plus 1 minus union rho n minus. So this is what is called Schur measure. So that's a product of two Schur functions, and there are two specializations applied to it, so to one Schur function and to another Schur function. So here these are all pluses on the left, here are all minuses on the right from your lambda. And finally, what this union means, so if you remember, one way to understand what is a specialization is by understanding how the power sums are being mapped. So when you computing the union of specializations, then what's really happening, an union of two specializations, rho 1 and rho 2, it is a map which maps the power sum pk into pk of rho 1 plus pk of rho 2. Yeah, kind of, yeah, yes. Exactly. So if you think about these parameters that, for example, last time were present in the Kerov's conjecture, then the parameters are you're taking union, but union with multiplicities. So if they're the same, then you just repeat this thing several times. OK. So we want to prove this theorem. And maybe actually we don't need a projector for some time. So let's turn it on, turn it off. Screen up. No, doesn't want to be up. This one? Yeah, OK. And we can mute the picture. So the proof of this theorem is based on the identity of symmetric functions, which is usually called skew-Cauchy identity. So let's formulate this identity as a proposition. I will not. Proposition. So it says that if you have two sets of variables, so you have x's, which are x1, x2, etc., and you have y's, which are y1, y2, etc. And then you fix also two Young diagrams, lambda and mu. And if you want to compute the sum over all nu's of s lambda over nu in x's times s mu over nu in y's. So in fact, that's a finite sum, because nu needs to be smaller than lambda and smaller than mu. But anyway, so to make it a little bit more infinite, we will multiply it by the product of all I and j of 1 minus xi yj inverse. And then the proposition is that it is actually equal to the sum over all etas of s eta over lambda of y times s eta over mu of x. So the difference between left and right-hand side is that, well, there's summations, but the Young diagram which we've been summed is jumping from bottom into top. And the specializations are also kind of exchanged. So here it has x and y, and then there is y and x. And there is some factor here, which we don't care much, actually. So in particular, if you take lambda and mu as being empty sets, so the Young diagram with all zeros, then what will happen with this identity? Yeah, this is just Schur identity. This is just Cauchy identity, because the left-hand side, this thing will be just a sum with one element. So that will be just one. And then there's some generalization which is called skew-Cauchy identity. Now, I don't want really to give you a proof. So one observation is that if you were closely following the yesterday's lecture of Alexey, then you should be able to produce a proof yourself. Just because really this situation when you have lambda and mu, and then there are two more Young diagrams. One of these is nu, and another is eta. It was really kind of a square that he was playing around the entire lecture. And the bijective proofs that he was given, they essentially were just bijective proofs for this identity. That's these bijections. That's one way how you can prove it.
It's the case when you have just one variable.
Yes, yes. You need to grow. That's true. That's true. Yeah. Another way to prove it, well, if you know just the Cauchy identity itself, when lambda and mu are empty Young diagram, then there is a way to produce this identity by kind of splitting the variables into several groups. Anyway, it will drive us too far if I go to the proof of that. So let's just assume that this identity is true. I can give you a reference if you want to read about it in more details. For example, in the book of Macdonald on symmetric functions and whole polynomials, there is a proof of that. Yes, and the examples. That's true. That's true. It's hidden there, but you can find it. Yeah, that's an exercise. Yeah. Okay, so that's one thing. Well, another thing is that we need to remember is kind of definition of the skew-Schur polynomials. There's a second identity which says that if you sum over mu as lambda over mu in variables x, and you multiply it by s mu in variables y, then this sum is equal to s lambda in x's and y's. So this is actually one of the ways to define skew-Schur polynomials I think that Alexey defined them through the combinatorial formula, but then there is kind of consequence, and there's this corollary of the combinatorial formula. OK, so given these two identities, let's try to prove this theorem. So, OK, so how do you really find the distribution of lambda k? Well, what does it mean that you need to find a distribution lambda k? Essentially, you just need to take this formula, then you need to do a summation over all Young diagrams except for the lambda k. So that's what I will try to do. So let's start, we will be summing sequentially one by one. So let's first sum over lambda 1. OK, so what are the factors that include lambda 1 in this thing? Well, you have this part of your picture, lambda 1 to mu1, which means that you have, is it visible when I write here? OK, that you have S lambda 1, and then you have S lambda 1 over mu1. OK, if you call it lambda 1 over empty set, which doesn't change anything, then you notice that this is precisely the sum of the form that we had in our Skew-Cauchy identity. Namely, this is this side. So these two guys are fixed. One of them is empty set, and another one is mu1. And this eta, that's precisely our lambda 1 that we are summing over. OK, good. So we can apply this identity. So if we apply it, then this sum becomes a different sum, which can now graphically we can draw in this way. So that is empty set mu1, and now this lambda 1 bar will be something which is smaller. So what do you get now? You get S empty set over lambda 1 bar multiplied by S mu1 over lambda 1 bar. Yes.
Times the equivalent of 1 minus.
Yes, times this thing, but this thing we just don't care at all, because it is some constant. It doesn't depend on lambdas or mu's or anything. So in the end, it will be absorbed into this normalization constant, which appears here. So we will not be even keeping track of that. OK, now when we have this thing, then what can you say about lambda 1 bar when you are summing over all lambda 1 bars here? It needs to be empty set, just because we have here empty set over lambda 1 bar, so it should be smaller than empty set. There is nothing smaller than empty set, except empty set itself. So the conclusion is that up to this factor, which is constant, so we don't care, what remains is this thing, mu1 over empty set, and which specialization? Well, there was this interchange of specialization, so that will be rho 0 plus, which appears here. So that's a result of summation over lambda 1. Now let's sum over mu1. So what remains about mu1? OK, so for the mu1, we have S mu1 at rho 0 plus. And then there were the factors which will remain in here. So that's lambda 2 over mu1. Lambda 2 over mu1. And that's a specialization rho 1 plus. OK, now here we need to sum over all mu1s. And you recognize that that's precisely the identity which is written on the left. OK? And then when you apply it, you see that the sum over all mu1s will be equal to S lambda 2 of rho 0 plus union rho 1 plus. OK, so what's the outcome? So we summed over lambda 1 and mu1. And what we saw that the result is actually the same picture of the same form, only these two guys disappeared. Now here we have empty set. And this specialization, instead of rho 1 plus, now it's rho 0 plus union with rho 1 plus. Again, then you can just iterate this process from this direction and similarly iterate it from this direction until finally you reach your lambda k. So at some moment you will reach the picture empty set, lambda k goes to empty set. And since the pluses are being united on the left, in the end you will have all the pluses which are on the left sitting on this arrow, and all the minuses sitting on this arrow, which are to the right. And that's precisely the formula that we are proving. Okay? So this proves this theorem. Yeah. Yeah, probably you're right. Well, you will need it to, I think you will need to use more complicated form if you want to look at the restriction to several guys. Like if you want to find joint distribution of maybe lambda 2 and lambda 5, then you will need really to apply the full power of this proposition.
We could use this argument to find out explicitly what zeta is?
Yeah, of course. So you just iterate it over and over again, and it will be just a product of these guys in the end, just specialized in a nice way. OK, good. So let's apply it to our setting of the Aztec diamond. So let's erase the proposition. We don't need it anymore. So let's just keep our Aztec diamond here. OK, so we apply it to the Aztec diamond, and we get that the distribution of lambda k is a Schur function of lambda k, which is specialized that you have alpha equals to 1 k times. Let's have a notation alpha equals to 1 to k, which means that you have k alpha variables. And then you multiply it by their, again, it's proportional, to their this thing into specialization beta equals to 1 and minus k plus 1 times. So that's just because all the down arrows, they are really betas. So we just compute all the betas which are on the right. And all the up arrows are alphas. So we combine all the alphas which are on the left. That's what you get. Yeah, so that is lambda. So I'm taking the up corner. That's true. Well, for the down corner, really, you can get the same, very similar theorem. I just don't want to write it on the blackboard. OK, good. So for the rest of the lecture, we will just concentrate on this measure. And we will try to understand, really, the asymptotic of this measure as k and m go to infinity. So that the Aztec diamond becomes huge, and you're looking somewhere in the middle. You want to say something. Namely, what really we will be looking at will be some kind of a law of large numbers for the measures of this type. So what do I mean by law of large numbers? So usually, we will be doing the following procedure. So this lambda, let's assume that it has k coordinates, lambda 1 greater than lambda 2 greater than lambda k. Now, for these k coordinates, we will think about them as about k points. And it is somewhat inconvenient that they might be the same. So we'll make a tiny shift in order to make them not equal to each other. So we will identify these k coordinates with an atomic measure of the form 1 over k sum y goes from 1 to k delta function on lambda I plus k minus I divided by k. Okay, so what's happened here? First, instead of lambda i's, we will have lambda i's plus k minus I. This is just innocent shift which helpful because lambda I plus k minus I, they're strictly decreasing. So that is just convenient. Now, okay, you have k numbers, and you kind of expect that each of them grows somehow in the order of k. So it's reasonable to normalize them by dividing by k if you want to see something finite in the limit. Okay.
You could have guessed to normalize by n.
Yeah, it doesn't matter because k and n, they will be linearly dependent one with another. So it's, yeah, it will be. I prefer to use k because I want this number to be the same as this number. So the theory will be developed in this form. And it's not very important, but just convenient for now. OK. Now, that's a point measure which kind of describes your section. Now, what really we will be proving that this measure, well, of course, it is still a random measure because lambdas are random. We will be proving that this random measure converges to something deterministic. That will be our theorem for today. There is some kind of law of large numbers which says that this measure becomes deterministic. And the way to think about it is really, OK, on the line, you have some points. And in the limit, these points start to have some density of this form. So there are regions where there are many points, and this will mean that this limiting density is high. And there are regions where there are no points, and this will mean that the density is very low. So this is kind of law of large numbers that we are going to be proving. So any questions about like general, philosophical setup? OK, if no question, then I will now define the main tool that we will be using for proving the law of large numbers for this measure and simultaneously for the huge amount of other measures. So the tool will be called Schur generating function. Let's have a definition. OK, so at this point, I will change notations a little bit. I will go back to elastic diamond at the end, and then the notations will be reversed. So if you have lambda 2 greater than lambda large n, so you have n particles this time, and you have a probability measure on these lambdas, p of lambda. Then you define the Schur generating function of these guys as the following formula. So that will be large S indexed by p. And by definition, that will be sum over all lambdas of p of lambda times Schur polynomial at lambda x1 xn divided by Schur polynomial at lambda 1, 1, 1. OK, that's a definition.
We have x1 xn also on the left.
Yes. Let's make it more explicit. Thank you. That's SP. OK, let's speculate a little bit about this formula.
So when you wrote p of lambda, were you meaning the full triangle or just one?
No, just this thing. So there's an n tuple of integers. So there is a probability measure on n tuples of integers.
Those are the parts of lambda.
Yes.
I thought it was.
Yeah. So these are numbers. Yeah. Yes. So we already kind of retreated ourselves to studying only one Young diagram, and now we are just looking at a single Young diagram. That's our object. OK, first, really, you are summing symmetric functions in variable x1 to xn. So the result is, again, a symmetric function in n variables. That's the first observation. Now, another observation is, OK, what really can we say about convergence of this series? Well, first, I claim that Okay, first a simple claim. If all x's are equal to 1, then it is the sum of all the p of lambda, so this is 1. So SP of all 1s is 1. Now, I claim that if you take all the xy's to have absolute value 1, so if you consider torus on the complex, in the complex space, then this thing is always convergent, no matter what you do with p of lambdas. So any ideas why that's true? Yes, but yeah, that's quite advanced proof that works this way. Now, if you are not as clever as Philippe is, then you can just say, okay, this thing is actually smaller than 1 if you take all the x's which are of absolute value 1. For example, you can look at the combinatorial formula for the Schur functions and notice that numerator and denominator are kind of the same. Yeah, that's true. Exactly. Well, unfortunately, that will not be quite enough for us. So we will need to be a little bit more advanced. So we will always assume silently that the convergence is not only on this torus, but actually in the neighborhood of this torus. So we will assume convergence in a neighborhood. I mean complex neighborhood of this thing.
Which is like to say that p decreases somewhat.
Yeah, exactly. So there is some kind of tail bound on this p, that there is no small decay in. Well, for example, in our case of the Aztec diamond, that is automatic just because really everything was finite. We have only finitely many configurations, so the sum is in that finite, well, it converges in all possible senses. Well, in higher generality, you need to assume. Maybe it's not important, but for now, our method works only in this scenario, when everything converges in a neighborhood. OK, so let's have an example of computing these Schur generating functions, and we will compute it for our Aztec. Yes, it doesn't matter. Yeah. OK, so we'll take this measure. So let us identify the notation. So the k will be a large n, and the small n will be some parameter alpha multiplied by the large n. Maybe alpha is a bad letter because I already had it. Let's have a. And this a will be greater than 1 just because k was smaller than small k was smaller than small n in the very beginning. And I claim that the Schur generating function, well, of this guy is equal to product y goes from 1 to n, 1 plus xi over 2 raised to the power a minus 1 times n plus 1. So very simple function in the end. OK, so how do you prove that? So proof. Well, OK, so what do we need to do? We need to take this measure, multiply it by the ratio of Schur polynomial in x's divided by Schur polynomial in all ones, and then do computation. Well, luckily, the thing Schur polynomial in all ones, that's precisely the thing which stays here. So they just cancel out. So what we need to do in the end is to sum over this guy lambda k s lambda k x1 xk multiplied by, let's have n already, multiplied by, well, the same guy here. And let's have lambda just to reduce the notations. S lambda of beta equals 1 Yeah, L minus 1 n plus 1. OK, so we need to compute this sum.
But that you have P of lambda k is lambda?
Yes, so this is proportional. So there is some normalization constant. You're correct. So there is some constant here, 1 over z, which in the very end we will understand how to compute it. But for now, we'll just keep it as some unknown constant.
Okay, but so in your claim, you have an equality.
Yes, exactly. Well, since this question arose, let me immediately say how you actually find this constant. Well, we have this property here that the Schur generating function at all ones should be equal to 1. So after we find the formula up to a constant, you just make sure that this function at all ones is equal to 1, and that's clearly the case for this function. So that's how we will find a constant in the very end. So because of that, I will be ignoring the constants throughout the proof. OK, so here is this thing. Well, if you know things about symmetric functions, then you will be able to immediately say that this is another type of Cauchy identity that is called dual Cauchy identity, which gives you the formula. Well, if you don't know much, then let me add a couple of lines how you actually do that. OK, so what you can write. Yeah, because you have these betas here. Yeah, we have betas. So exactly. So when you take the transpose, and so it kind of becomes dual. Yes, exactly. So if you don't know about these things, then, well, what you can do? Well, you can say, OK, we start with usual Cauchy identity in lambdas, and then you need to specialize it in these betas. So in other words, you take the specialization in variables y's, this specialization, beta equals 1, alpha minus 1, n plus 1, of the kernel of the usual Cauchy identity, of the product 1 minus xi yj, the minus 1. OK, so what's written here? Well, the following thing is written. So assume that instead of x's and specialization, you have x's and y's here. Then we know how to sum overall lambdas. That's precisely Cauchy identity, and then gives this thing. But now we need to apply our specialization in this group of variables in y's. And that's what is written here. So you apply the specialization in these betas in the y variables. OK, so first, well, that's multiplicative, and specializations, by the definition, they're homomorphisms. So you can factor the things. So you can say that this is product over I of, well, rho y, beta equals to 1, and then there will be product over j, 1 minus xi yj power minus 1, and everything is raised to the power alpha minus 1 n plus 1. So what's happened here? First, I factorized with respect to x's. And in addition, I used the thing that when you have several betas, then you can write it as a single beta and then raise it to the higher power. That's because when you compute a union of several specializations, then this thing in the Cauchy identity is just multiplied. Well, if you don't follow, then don't worry. I mean, we'll use this fact, but we will never use the proof afterwards. OK, so it just remains to compute this thing. OK, how do you compute this thing? Well, this product, 1 minus xi yj, it can be decomposed into a sum. So this is a sum of xi to the m. M goes from 0 to infinity, times the mth complete symmetric function in y's. So why is that? Well, essentially, you just take this inverse power. You use the geometric series formula. This is 1 plus xiyj squared, etc. And then you multiply all the things, and you collect the coefficient of xi to the m. And you immediately recognize that that's a complete symmetric function which appears in this decomposition. OK, good. So now the only thing which remains is now to compute this specialization in beta equals to 1 on the complete homogeneous symmetric function. Well, and that is easy again, because by the definition, the beta specialization on a complete symmetric function is the same as alpha specialization on the elementary symmetric function. So that's a formula which I think Alexey used as a definition, actually, of beta specialization, that if you specialize beta equals to 1, complete symmetric function hm, then it is the same as specializing alpha equals to 1, elementary symmetric function em. OK, now, elementary symmetric function, this is something that everybody understands, it's just product of all variables. Specialization in all alpha equals 1, that is also something that everybody understands, because it just means that you plug in the first variable x1 equals to 1, and all other variables equal to 0. So what's happening with elementary symmetric functions if you plug in one variable equal to 1 and all other variables equal to 0? Exactly. So the first two are equal to 1. Zero's function is 1 by definition. The first one, that is the sum of all variables, that is 1 by this becomes 1. Or the larger one, they have products of some amount of these guys, so they all die. OK, so the conclusion is that this is precisely equal to 1 plus xi. Because you specialize by beta these guys, and only first two guys survive, so that's 1 plus xi. Well, good, but that's precisely our formula here. Because we had product of 1 plus xi raised to this power. Well, we need this normalization constant, but as I told you already, that's just figure it out because the value at all ones is equal to 1. OK, so this example shows you that, well, indeed, you can compute these guys. OK, now, if we believe that we can compute these guys, then the next question, OK, how is it useful? How can these guys help us to find the law of large numbers? And that will be our next topic. So what's the time? OK. So let's jump to it. So what do we need to keep? So I think that we no longer need to keep the formula, the yardstick diamond. What we want to keep is the formula for its Schur generating function, because somewhere at the very end of the lecture, we will use it. So let's keep this formula. OK. And let's try to think, OK, how do you really extract some asymptotic information out of the Schur generating function? Well, in the end, we will want this large n to be growing to infinity. But let's start from the toy example. Suppose that it's not growing at all. Well, maybe. Why not? Let's try. So what if just n was equal to 1? Then your generating function is very simple. You have a random variable xi, and you have some probabilities that this xi is equal to a number, small n. And you have a generating function f of x, which is sum of x to the n p of x. OK, and you want to extract some information about xi out of this generating function. Well, then there is a very simple way how to do it. Namely, if you take this function as a function of x, and then you apply to it a differential operator, x ddx raised to the power m, apply it to your function f of x. And then after applying, you will set x equals to 1. Then what you get? Well, let's see what you get. X ddx, this x on the monomial, is an eigenfunction. And the factor that appears is precisely n. So there will be several of these guys n's. Afterwards, when you set x equals to 1, then all the x to the n's will disappear, because x is set equal to 1. So the result is that it is equal to sum n to the m times f of x, just sum n to the n times p of n. Or you can interpret this thing in terms of your random variable xi as expectation of xi to the mth power. Okay. So you take Schur generating function, you act on it with this simple operator, and you get expectation of your random variable. You know, really, if you know all these expectations, then you know everything about your random variables. Well, for example, there is simple, well-known lemma which says that if you have a sequence of random variables, xi1, xi2, etc., and you know that expectation of this xi to the power q converges to the expectation of some other random variable xi to the q, and if you have some technical restrictions that these guys do not grow too fast, then this immediately implies that these random variables converge in distribution to random variable xi. Yeah. Thank you. So plus technical condition, I don't want to write it on the blackboard, and then xi converges to xi in distribution. Well, in words, it says that if you know convergence of the moments of your random variable, then you know everything. You know the convergence of distributions. So in a sense, convergence of the moments is stronger than convergence of distributions. Okay, so the whole idea is just to mimic exactly the same approach, but now for the Schur generating functions. That will be, the whole idea of everything that will be happening for the next 2 lectures. Okay, so for this approach, there were 2 ingredients. First, generating function, which is already here. And second, this differential operator, which was useful. So what will replace the differential operator here? So that's a new differential operator, which is working nicely with Schur function. That will be our next definition. It will be operator, we'll call it dm. And that will be equal to the product over I smaller than j, xi minus xj inverse, times sum, y goes from 1 to n, xi ddxi to the m, and times product xi minus xj. So in other words, how this operator acts on the function? First, it multiplies the function by the product of the differences of all the variables. Then it acts by this differential guy, and then it divides back by this thing. So that's how it works. Okay, why is it nice? That's because of the lemma. Which says that if you act with this operator on Schur function, then what you get is a sum of lambda I plus n minus I to the mth power multiplied by the same Schur function. Okay, how do you prove it? Well, to prove it, of course, you need definition of Schur function. And that's essentially it. So what is the definition of Schur function? So that's a determinant of xi raised to the power lambda j plus n minus j divided divided by the product xi minus xj. Okay, so you can see that actually two definitions are well adapted to each other. That when you multiply, the denominator disappears. And so dm s lambda is equal to this product xi minus xj inverse times this guy, sum xi ddxi to the power m, computed on the determinant, that xi to the lambda j plus n minus j. Okay, now let's see what's happening when you apply this operator to this determinant. Well, really, what is the determinant? It is the alternating sum of n factorial monomials. Now, each monomial will have the following form. Well, there will be n variables x's, and each of them will be raised to some power, one of these lambda j plus n minus j's. So your operator really will care only about one of those guys. So there will be n factors, but only one variable appears here. So it will act on this unique factor, and it will produce precisely lambda j plus n minus j raised to the power m. Because that's precisely the same computation that I just erased, just one-dimensional computation. And then when you sum over all guys from 1 to n, then you will get the sum of all these things. So you get that this is precisely product xi minus xj inverse times sum lambda I plus n minus m to the m times determinant. And that's your Schur function multiplied by this thing. Is it fine?
So you're saying that the n is an operator on polynomials and symmetric functions are.
Well, Schur symmetric functions are eigenspatients. So this is Schur polynomial, which is eigenvector. Yeah, there will be not eigenspace. I mean, so because eigenvalues are different depending on the thing.
You can find Schur functions as the eigenvectors.
Exactly, that you can do, and that is actually a very nice approach, because if you want to go more complicated to, for example, Macdonald polynomials, then that's precisely how people define them. So they start with some operator, well, a little bit more complicated than these ones, and then they define polynomials as eigenfunctions of this operator. So that's true. You can just use it as definition of Schur functions if you prefer. OK, good. Now, really, it means that in order to extract some information about Schur generating functions, what you need to do is to apply these operators to your Schur generating functions, and then you will get some information about your measure. OK, so before we start going into technical details, let me state the main theorem, which is maybe the most important result. OK, so the theorem tells you the following. Suppose that as n goes to infinity, you know something about Schur generating function. So suppose as n goes to infinity, well, I mean that for each n, you have some probability measure. And you know that the Schur generating function corresponding to these probability measures have some nice properties. Namely, you will know that 1 over n times ddx1 to the k of the logarithm of your Schur generating function evaluated at all x's equal to 1, that this converges to some constant ck. That's first. What?
Just one differential?
Yes, so this is a function in n variables, and you differentiate it only with respect to the first variable. Yes, and this should hold for each k. So you have a sequence of these numbers, ck's. Second property is that if you differentiate in more than one variable, well, that is something general so far. So these c's, they will depend on everything. So all the information is now encoded in these c's. Well, what I want to say now, I want to formulate a theorem which will extract the law of large numbers or some asymptotic information out of the behavior of Schur generating functions. That's a general aim.
Your formula, peak may depend on n, or?
Yeah, it depends on n, of course. For each n, you have a probability measure on n tuples of integers. They are, of course, different just because the state spaces are different. And for each of them, you compute your Schur generating function, and then there is a limit formula. What? Yes. So let's call it Pn maybe. And in addition, we will assume that 1 over n times the product equals 1 to k d dx ya. Maybe a is bad. I just used a. Let's have b. Again, of the same logarithm of Spn, this converges to 0 as long as this set of indices x, y, b, let's have k here, is larger than 1. In other words, what's written here? So if you differentiate with respect to one variable, then after normalization you have a limit. And if you differentiate with respect to at least two variables, so maybe more, 3, 4, etc., any finite collection, then the limit should be 0.
You make the same assumption that x1, x3.
Yes. That's, thank you.
And then you need to check it for the first case.
Yeah, that's the same assumption, yes.
But you just need to check it for the first case.
Yes. So in the same form here, of course, you can differentiate with respect to second variable, third variable. It doesn't matter because everything is symmetric. I just wrote, first variable for simplicity. Okay, so we assume that this is true. And now the theorem tells you that if you know this, then there is a law of large numbers in the following form. So then, again, for each k, 1 over n times sum 1 to m lambda I plus n minus I divided by n raised to the power k converges, well, say in probability, which we will prove in a stronger sense, to some numbers p of k. So what does it mean? So if you remember this identification of our n tuple of integers with a probability measure, 1 over n sum delta lambda I plus n minus I divided by n, then this sum is just a moment of this probability measure. So this sum is integral of x to the k of this measure of dx. So the moments of this probability measure, each of them is a random variable because lambda is a random variable. It even depends on n. So this random variable, the statement is that these random variables will converge in probabilities to non-random numbers. So these are numbers. And moreover, we have a nice formula for these numbers. So let's write this formula. So P of k is a coefficient of Z inverse in 1 over k plus 1 times 1 over Z plus 1 times 1 plus Z divided by Z plus 1 plus Z multiplied by the sum. B goes from 1 to infinity. CB Z to the B minus 1 divided by B minus 1 factorial, and everything raised to the power k plus 1. OK, so what's written here? So we start with our coefficient c's. We make an exponential generating function out of these coefficients. So sum zb minus 1 times cb divided by b minus 1 factorial. Then we do some strange manipulations with this generating function. We multiply it by 1 plus z, add 1 plus z over z, raise to the power k plus 1, remove back 1 power of z plus 1, divide by k plus 1. The result is still some series in 1 over z. And you compute the coefficient of z inverse in this series. So that's a formula. Or some people prefer contour integrals. If you prefer contour integrals, then you can write it in the form that is 1 over 2 pi I, 1 over k plus 1 of the integral dz. No, the integral will be just the same. So for yes, the formula is, well, yes, it is some kind of that. That's how it's obtained. It's some version of that. It's some version of that. I mean, no. Well, you're making changes. 1 plus z over z. Raised to the power k plus 1 again. So that's if you prefer to extract your thing as a contour integral. Well, in a sense, this formula is sometimes better, but in order to use it, you need to assume that this series is convergent. That's one disadvantage. On the other hand, it's advantage that it's easy kind of to manipulate with the formulas of this kind, and you integrate it around the 0. Well, on the other hand, this formula has purely formal meaning, so you don't need to assume anything, any convergence. So it's important to know that there are these two meanings. Either you can compute contour integrals, or you can write this as a series, but these two meanings are completely equivalent.
What's the radius of the integral?
That's around 0. So that's absolute value of z is small number epsilon. So you integrate only around 0. OK, so that's our theorem. So what's happening with time? It's fine. OK, so let's start proving this theorem.
You prove it for a generic generating function.
Yeah, exactly, generic. So in the end, we will use it for that, guys, for the ASEC, but the power of the theorem is, of course, that it's completely generic. You don't need to know anything. Well, the only thing that you actually need to know is this thing that I told you, that I always silently assume that everything is convergent in a neighborhood. And this is actually kind of important here, because if it's not convergent in the neighborhood, then it's not even clear what's written here. But if it's convergent only on the unit circle, then what does it mean that you take derivative with respect to the first variable?
Well, it could be convergent on a disk, and the derivative is done inside.
It's probably, maybe. I mean, probably everything holds even if it converges only on their unit circle. Only that's more technical, and we never tried to do it. But then you need to reformulate it in a more tricky way, because in principle you can compute the derivative along the circle. Well, it's possible. You can differentiate in this direction. But then it shouldn't be the derivative d dx1. You should write it in somewhat different form. Well, the convergence of moments will immediately imply that these things as measures weakly converge to a limit. So in this sense, they do weakly converge to a deterministic limit. Yeah. You can think about them in this form, yes. Well, if you think, there are limits of the moments. Yeah, there are limits of moments. So degeneration might happen. That's true. But if you don't, if you have, I don't know, if you are bounded somewhere or something, then if generation doesn't happen, then there should be a measure there. Well, just because the set of measures is a compact set, unless something escapes to the infinity. So if you don't allow things to escape to the infinity, there is no choice. Well, it needs to converge to some measure. OK, so proof will consist of two steps. So first step will be proving that n to the minus k plus 1 times expectation of the sum lambda I plus n minus I to the k converges to the number p of k. So the first step we would prove in convergence of expectations. And the second step will be to prove that indeed you have concentration in probability, that when you subtract the expectation, things converge to 0. So I think that today we will have time only for the first step, and the second step will be part of more general theorem next time. So we will be only proving this thing today. OK. So we already know how to compute this guy, my expectation with respect to our probability measure. We'll know that this is dk of sp, and then all variables are specialized to 1. So that was a consequence of our things with differential operators, and that trick that I showed you with functions in one variable. So if you take Schur generating function, you apply to it your operator, then these factors pop out, and then you plug in all the variables equal to 1, so the Schur functions will disappear, and what remains will be precisely this expectation. OK? OK, so, well, we need just to compute this. Now, the question is really, how do you apply your operator? So product xi minus xj times sum xi di to the k times product xi minus sj times sp yeah, there is an inverse somewhere here. Yeah, thank you. OK, so let's think about it. So this is some differentiation. We always have Leibniz rule for applying derivatives. In other words, it means that what are the options? Well, maybe you can differentiate one of these factors Or maybe you can differentiate this guy. These are the only two options. Now, in the end, you will divide it back by xi minus xj, which means that when actually you differentiate one of these factors, well, the factor kind of disappears. It's replaced by xi. But then in the end, you will be dividing by these guys, which means that if you really differentiate one of these guys, it leads to appearance of the product xi minus xj in denominator. So let's write it in this form. So you can differentiate xi minus xj, and it will lead to the appearance of xi divided by xi minus xj in the end. Well, what else can you differentiate? Well, because there is xi di. Xi di. OK, other thing which might happen. Let's separate this xi. Let's get 1. Well, other thing which might happen is that, well, maybe you apply this xi di. It's raised to the power k. So maybe you apply it once, and when second time you apply it, then this di might act on the xi which appeared before. Well, that's also a possibility in the Leibniz rule. So you differentiate xi from other xi di. Well, then the third case is that if you differentiate sp, and maybe several times you differentiate sp. OK, now, next thing that we want to do, we want to write everything in terms of the logarithms, because as you noted, our theorem is really about logarithms of generating function, not about generating function itself. So how do you write everything in terms of the logarithms? Well, that's a very, very simple trick. You just say that sp is actually exponent of the logarithm of sp. Yeah, not too hard. And then, well, you can differentiate this identity and get that this is equal to dy to the logarithm of sp times sp. Nothing complicated, but somehow it's a critical step in all what we are doing. So it means that when we differentiate sp, we kind of have some kind of eigenrelation. Because really, sp remains again, and you get some new factor, dy logarithm of sp popping out. Logarithm of sp popping out. OK, now the conclusion is that after you really apply the Leibniz rule to this guy many, many times, the result will be a sum of the terms of the following form. So this is equal to their, let's write it just. dksp is a sum of terms which look as follows. So sp will pop out no matter what, because you differentiate this guy, then you differentiate again. Well, you again apply the same trick, so sp will pop out. Now there will be some number, some power of xi's, because they are here. So it will be xi to the power k minus q. So if you never went into the second case, then there will be precisely k of these xi's. So that's the maximum possible thing. But in general, you might have differentiated xi some number of times. So that's k minus q. Now you differentiated your logarithm some number of times. So product 1 equals 1 to infinity di to the power nu a. Yes, it will be taken into account to this formula which I will write now. That's correct. You don't need to mess up two cases. You shouldn't do it. And then there will be xi minus xj1, xi minus xj2, etc. xi minus xj. So that's a claim that no matter what you do, after you apply Leibniz rule in its full power, the result will be a sum of the terms of this kind. So let's stare on it for a second. If somebody disagrees, please raise your hand, and then we will try to. Well, because really that's. Everybody disagrees? Is it the thing? Yes, yes. All the j's needs to be distinct. That's correct. And so the idea is very simple. So sometimes we differentiate these guys, then we produce these guys. Sometimes we differentiate x's, and then we produce these guys. And sometimes we differentiate, SPs, and by using these tricks, that's always some combination of derivatives of the logarithms. Oh yeah. There are tons of combinatorial coefficients. Of course, each term will appear a huge number of times. Well, the only thing that is somewhat important here, all these parameters, they're linked together. So Q plus M plus sum of new A's, that is always equal to K. So that's the total number that we differentiated. OK, good. Now, in the very end, what do we need to do? We need to plug in all x's equal to 1 into this formula. Well, there is one term where it's particularly nice. It is SP. SP, we know, well, it's SP of all ones is 1. Very nice. Yeah, that is not too good. Yeah, exactly. So plug in all the ones here. Somehow tricky, because you see that they're in denominator. So at first, it seems that everything explodes. So need to plug all of them equal to 1. OK. Now, the trick for plugging in is to remember that indeed, as people just told, well, there are lots of signs, and there are lots of terms like that. More precisely, well, at the very beginning, our operator was completely symmetric. Really, if you just interchange xi and xj, nothing will happen. The sign will pop out here, and the same sign will pop out here. Well, what it means is that every time we have a term of this kind, we also have all the permutations of the indices. So you can symmetrize this thing. And it's also, these terms also appear somewhere in our sum. So the term of this kind, never comes alone. It always comes with other guys, and hopefully these other guys will help us. So let's see.
So the differential operator is acting on a function which is completely anti-symmetric, because it's a symmetric 1 times 1.
No, SP is symmetric. I mean, if you treat dk, if you treat dm as an operator, then the operator is symmetric, and the function which we apply it to is also symmetric. So everything is symmetric here. Because of that, no matter what sum we get, the sum is always going to be symmetric as well.
So I thought you were concentrating on x to the power k acting on.
No, it's a simple. Yeah, yes. We want to look at the whole thing. That's true. OK, so it is symmetric. Now let's try to understand that. Really, the fact that it's symmetric saves the day. So let's consider the simplest possible case, which appears here. So out of these guys, what is the simplest possible case? Well, that is this guy. That is xi to the k sp times di to the k minus 1 logarithm sp, and then xi minus xj. So that's the simplest possible case when there is only one guy in denominator, and there is only one product here and no Q at all. So that's the simplest possible thing which can appear here. Well, since everything is symmetric, then together with this term, we will have its permutation, which will be xj to the k, dj k minus 1, logarithm fp, same xp, divided by xj minus xi. So when we add two of these guys together, well, sp we don't care. It's symmetric. It will disappear in the very end. And when we add it, it is with minus, and this one is in this plus xi di to the k minus 1 logarithm sp. And then you realize that this is actually convergent when xi and xj goes to 1. It just has a limit, and the limit will be just derivative of this guy at a point where both variables are equal to 1. But this is just a formula for derivative when you send the variables to be equal to each other. Okay, that's a general idea that after you symmetrize, all the exploding things will disappear, and the limit will be finite. Now let's formulate this observation as a lemma. Let's have it as a lemma. So let's call this term somehow star. And the statement is that if you symmetrize your star with respect to variables I, j1, jm, so you take this and you take all the possible permutations of the m plus 1 variables that you have here, and you add all the results. Then this has a well-defined limit. So has a limit as xy, xj1, xjm go to 1. And moreover, this limit is a finite, which is a finite sum of m plus first of, how to say it, partial derivatives of numerator. At 1. Okay, so what is meant here? Well, look here. So we took this guy, then we wrote xi, we sent xi equals to xj, and then we sent everything equal to be equal to 1. So the result will be a derivative of this guy again at 1. So and then the result of symmetrization and setting of variables to 1 is just another derivative at 1. Now this lemma says that it is true in general that no matter what you do, the result will be some combination of partial derivatives at 1. That's what I'm trying to prove now.
The most general function we want to apply is some f of x divided by product of x minus yj.
No. Our function is always this thing. That's what I mean. So we always apply to.
The one at the numerator is so general that in fact.
Yes, numerator is general, but what is important that this function numerator is well defined in a neighborhood of 1. So really, sp was a Schur generating function which was convergent at point 1, and we assume that it's also convergent in a neighborhood. So it is well defined and close to 1 in a neighborhood of 1. So the logarithm is always well defined analytic function in a neighborhood of 1. So these are the functions to which we apply these lemmas. So a function which are analytic in a neighborhood of all 1s. Oh yeah. So we are not going to look at this numerator exactly. You're right. It's not important what is numerator here. So how do we prove this lemma? Well, it'll be somewhat sketchy proof, so I will not prove one of the technical estimates, but it's doable. So we will expand the numerator, this thing that we want to apply it to, as some power series. Sum of A M, where M is multi-index, times product. A goes from 1 to A, XA minus 1 times MA. Okay, so I just say, okay, numerator is some analytic function in the neighborhood of 1. Now, any analytic function in the neighborhood of 1 can be decomposed into a series. And that's what I wrote here. Just decompose everything into a series. Okay. Now, you can now start applying these operators to this series just term by term, because everything is linear. And because of that, it's in fact enough to figure out this symmetrization property just for polynomials. Okay? Or even maybe monomials to reduce to polynomials. Okay, now if we work with polynomials, then what do we want to do? We want to symmetrize some function of k variables divided by x1 minus x2, x1 minus xk. And we want to understand that if you do this symmetrization, then you should be able to plug in all the variables equal to 1 after you do this symmetrization, and there are no explosions. That's what we want to understand. Okay, let's just rewrite it in a bit different form. There is a sum over all permutations minus 1 to the sign of this permutation. This permutation applied to f of x1 xk divided by x1 minus x2 x1 minus xk times product xi minus xj, I smaller than j, and divided by the product xi minus xj. Okay, so what's happened here? Well, I really wanted just to symmetrize this guy, to sum over all permutations of its indices. But I reduce symmetrization to anti-symmetrization by noting that if we multiply our guy by this product of all the differences, and when you interchange two of the indices here, then the sign will pop out. And then this thing will be the same. So this is the sign which pops out, and then I divide back by this thing. Okay? So this is just an identity, how symmetrization can be written as anti-symmetrization. Okay, now after you do this, you can notice that here, well, you can just cancel the factors. So after you cancel the factors, the result is still a polynomial. Now you take a polynomial and you skew symmetrize it. So you do anti-symmetrization of this thing. Well, the result, pretty much by the definition, will be skew symmetric polynomial, which is changes its sign when you interchange two variables. Now, if you have any antisymmetric polynomial, then it vanishes when xi is equal to xj, so it's divisible by the all xi's minus xj. So you divide this antisymmetric polynomial by this thing, and you get a symmetric polynomial. Okay. So therefore, well, the result is symmetric polynomial. Well, if the result is symmetric polynomial, of course, any symmetric polynomial has a limit as you send all variables to be equal to 1. As well, it's continuous everywhere. That's one observation. Another observation is that well, really here, we know something. Namely, if this thing had a negative degree, so if degree of numerator was smaller than degree of denominator, then this thing, after you multiply by this thing, by these factors, will be a polynomial of degree smaller than k choose 2. If it's smaller than k choose 2, then after skew symmetrization, the only thing you can get is 0. That's because it should be divisible by this guy, and the degree is not large enough. Because of that, you can actually figure out that, well, when you afterwards want to plug in all x is equal to 1, and if you are dealing with these monomials of the form xa minus 1 to the power ma, then the only case when you can get non-zero is the case when sum of all these degrees is precisely equal, well, to k in this case, just by the counting the degrees. OK, so that's the idea of this lemma. So because of that, the symmetrization is fine. So if you expand on the monomial, then you see that polynomial is going to polynomial, so it has a limit. And then the only last step which remains is to think a little bit about changing the order of summation and applying these operators. But this can be done. I don't want to get into details about that. OK, so the proof was a little bit sketchy, but I hope that everybody believes in the lemma in the end. Yes, so this is, I mean, degree in this expansion. This is just because if you were divisible to enough of xi minus 1s, then they will just still be there after you do skew symmetrization. You just count, what's the order of this 0, and you see that the order of 0, if the order of 0 in numerator is larger than k choose 2, then after you cancel with k choose 2, it will be still there. OK, so well, we believe in this lemma, and let's remove its sketchy proof, not to embarrass me anymore. OK, so we know that these guys in the end will not explode. That's the only conclusion of the lemma which is important for us. That they're fine, they're not exploding. Now, as was mentioned at the very beginning, really these guys, they come with a huge number of combinatorial terms. So let's try to, and what we want to do in the end, we want just a leading contribution. Because we will renormalize by n to the minus k plus 1. So if terms of some kind, if there are not too many of them, then it will just disappear in the limit. So we want to understand which terms will really give us a leading contribution. Because of that, let's compute what are the combinatorial coefficients appearing here. Well, first of all, notice that, well, we need to choose these indices here, y, j1, j2, up to jm. So we need to choose m plus 1 indices. Since everything was symmetric, in principle, these indices can be anything, any numbers from 1 to large n. Because of that, there is a combinatorial factor of order. There's a combinatorial factor of order n to the m plus 1, again, up to some constants. Because n choose m, that is something in large n expansion that is of order n to the m plus 1. OK, that is one thing. Now, after you do this, how large is this term? Well, in order to understand how large this term is, we need to turn to our theorem. So what this theorem tells us, that well, no matter how many times you differentiate your logarithm, the result is still of order n. Okay? Well, what it means is that here, each of these factors will produce something of order n. Okay, so there will be combinatorial factor n to the m plus 1, and then there will be n to the number of non-zero new a's, just appearing because of the growth of derivatives. So the conclusion is that contribution of the term of this kind is n to the m plus 1 plus number of non-zero new a's. Okay, now a combinatorial question that even those who are fallen asleep already hopefully should be able to understand. So what if we want to maximize this thing? We want leading order, so we want to maximize m plus 1 plus some of the non-zero new a's over what set? Well, what we know is that q plus m plus some of the new a's is equal to k, and all these numbers are non-negative integers. So my question is, okay, when is it maximized? Yes, so q shouldn't be there. It doesn't help. So q is equal to 0. And all news, well, they need to be equal to 1. Otherwise, again, it's only getting worse. So that is when it's maximized. Let's write it here. At q equals to 0 and new 1 is equal to new L is equal to 1. Okay. Well, this simple combinatorial thing leads to the fact that about other terms we don't need to care at all. We just need to care about one particular kind of term here. And let's write it down, what it is. It is x1 to the k d1 logarithm sp to the L, and then divided by x1 minus x2, x1 minus x3, x1 minus xm plus 1. And here L plus m is probably k. Well, here we don't quite use it. I mean, it will be, it's kind of, yes, we don't really use it, that's true. Only thing that we are using is that other terms are not exploding. That's we kind of know, because we ignored them without computing them. So we need to understand that they're finite, and that is guaranteed by this lemma in the end. Okay, so we just need to compute now symmetrization of this guy. So the lemma was very abstract. It wasn't telling me what is the result of this symmetrization. Now, if we want to arrive at an answer, then we really need to, for this particular guy, we need to find what is the limit of the symmetrization. And that will be the content of another lemma. I need to erase something. I want to understand. So how much time do we have? Another 10 minutes. Okay, so let's write it on the same place. So this lemma will be telling us that limit as xi goes to 1 of some function g of x1 divided by x1 minus x2, x1 minus xn plus n minus 1 terms obtained by switching x1 with some variable xi. So you take a function g of x1 of only one variable, you divide it by x1 minus 2, x1 minus xn. It's kind of the form that you have here, because here everything depends on the first variable at the end. Not exactly, but I will clarify that a little bit. So if you want to compute this kind of thing, you symmetrize and you compute the limit, then the answer is given by dn minus 1 dz. Well, this thing is already symmetric at x2 and xn. So I only need to symmetrize so that the x1 has the same role which all other guys. So this is g of x1, and then you interchange x1 with each of the other variables. That's what is written here. So this is equal to n minus first derivative of g of z divided by n minus 1 factorial, and at z equals to 1. That's the lemma. Okay, in a sense, if you think about it, we almost know this already. At least we already know that it should be derivative of this order. So that was the content of the previous lemma. Now, we don't know the exact formula so far. But how do we figure out exact formula? Well, it is also kind of easy here. We already know that the result is continuous. So after you do all this, sum all these guys, the result is continuous at all x's. It is continuous at all x's. You can approach it from any direction. So you choose some particular direction. Maybe xi is equal to 1 plus epsilon times y minus I, times y minus 1. And after you approach it from this direction, you can just Taylor expand your function g. You say that g of 1 plus epsilon a minus 1 equal g of 1 plus g prime of 1 epsilon a minus 1 plus etc. So you expand it up to this order. Well, then you need to plug in it into here. Then you need to collect all the terms, and you will get the result. Well, I don't want to torture you with that. That is just some combinatorial coefficients and some summations of combinatorial coefficients. Maybe there is a simpler way. I don't know. I mean, OK. So if you don't like this way, then you ask Christian. He will give you a simple way. Or if you want to look at our article with Alexey, so we have an article of Bufetov and Gorin, which is called Representations of Classical Regroups and something there. So it starts with representations. And it is lemma 5.5 there. But really, this is just some operations with binomial coefficients. Just, it's impossible to do it on the blackboard, I'm afraid. OK, now, corollary of this lemma is that if you take this guy and you again add to it all the permutations, so plus m terms when x1 was swapped with some other guy, and you send xi's to 1, then the result is equal to ddx1 to the m times x1 to the k d1 of the logarithm sp to the l, and then divided by m factorial. And then all xi's equal to 1 plus O small of n to the L minus 1. Okay, let me clarify it a little bit, because it is almost this lemma, but not exactly. Really, the difference is that here in this lemma, we're working with a true function in one variable. Now, this thing, it kind of, in the first variable, but not exactly. Somehow it depends on all the other variables. OK, but on the other hand, well, what do we know? We already know about the general statement before that no matter what, by the result of this symmetrization, should be a sum of partial derivatives of this order, precisely of this order. Now, what are the partial derivatives of this order? Either you differentiate only with respect to this first variable, and that will be this answer, or you also differentiate with respect to some other variables. But luckily, if you try to differentiate with respect to some other variables, then we already know that the contribution is of lower order. And because of that, you can just ignore these guys. So the only guys which you have to keep is the guys where you differentiate only with respect to first variable. And this is precisely given by this lemma. So that's how it works. So any questions about this transition? Maybe it's better not to write O large but O small of n to the L, because that's the notations we have in this theorem. OK, so we're already at our conclusion at this point. What? It's a, yes, I wanted to say that it is small o of n to the, what do I want to say? Yes, of n to the L, yeah. Actually, no, it's something, should it be like that? No, it should be, yeah, this L and this L should be the same, yeah. So this is of order L, n to the L, and this is of smaller order. That's what I wanted to say. OK, so here's the conclusion. After all this so conclusion. Well, the conclusion tells us that when you apply our operator dk to the SP, and we plug in the variables equal to 1, then the result is n to the k plus 1 times sum over L going from 0 to k plus 1, k factorial divided by L factorial, L plus 1 factorial, k minus L factorial, d1 to the L of x1 to the k, and then d1 logarithm sp to the k minus L. And then all variables are equal to 1 here. OK, so what's the difference with what we had before? So we already figured out this term. That's precisely this guy. So the only new information here, these are these binomial coefficients. Well, how do they appear? Well, that's because I never was carefully taking account all the combinatorial factors. I was telling you that something is of the order like n to the number of times, but actually there is a binomial coefficient rather than n to the power. And here I just reconstruct all the binomial coefficients. So nothing else happened. Just really the number of ways to choose like these indices out of the all indices, that's all what's happening here. And of course, there is a remainder in the formula. Large, small, O over n to the k. OK, so since the time is essentially over, Let me think. So let's have a vote. So this is a form which is not yet the form of the theorem. There is already some answer, so we found the limit. So after you divide by n to the k plus 1, you get this limit. So almost the form of the theorem. So what remains is to match one to another. Well, I think that the audience is tired enough. So let's decide that I will match it at the beginning of the next lecture on the next Tuesday. So this is something combinatorial, and that is kind of like Philippe was saying, some version of inversion formula. This can be done. OK, so see you next Tuesday.